All right. Here we are, 2.2, definition of limits. We're going to find limits from graphs and tables. We're going to do a little bit of one-sided limit, existence of limits, and look at the greatest integer function. First of all, limits. Preliminary definition of a limit. Suppose the function f is defined for all x near a, except possibly at a. So this is just an x value a. If f of x is arbitrarily close to L, as close as we'd like it to be, for all x sufficiently close, but not equal to a, we write that the limit as x approaches a of f of x equals L. Basically this. All that we're saying is that as x approaches some value a, our function is approaching some y value L. I'll show you that in a minute on a graphic. Say that the limit of f of x as x approaches a equals L. This is how we would verbally describe this notation right here. The graph approaches a value L as the graph approaches a particular x value. So let me just sketch something for you. It's wordy, but it has a very simple meaning when you see it on a graph. Okay, so let's say we have a graph, and here is A. Okay, so as our x value approaches A from either side, right, so the limit as x approaches a for f of x, this function f of x, this is our function f of x, all that it's saying is that the limit is approaching some y value L. Okay, so as x approaches a, y approaches L. L is just a y value. All right, so let's find the following values using the graph. Now this isn't limits yet, I'm just looking for output values. So for f of 0, well, if x equals 0, looks like y equals 1. What if f equals 3? Or excuse me, x equals 3. Don't be fooled. When x equals 3, our function value is negative 1. So there could be some like jump discontinuity. This is a replaceable discontinuity. There's different words for it. And just wanted to think about what would f of negative 2 equal. You can pause the video or just think about it. F of negative 2 is 2. Okay, so now let's look at a function and fill in its table and see if we can make some connections here. So let's complete this table, just filling in y values for g of t. So let's plug in values. If I plug in 0, g of 0, looks like I'll get negative 9 over negative 3, which is 3. What if I plug in 1? Well, that'd be 1 minus 9, which is negative 8. Negative 8 over negative 2 is 4, okay? What about g of 2? G of 2 would be 4 minus 9, which is negative 5. Over 2 minus 3, which is negative 1, which is equal to 5. So you kind of see what's going on here. That should be a 5. Now the temptation is to say, oh, hey, it's going to be g of 3. It was going to be 6. No, it's not. Okay, so g of 3, if I square 3, I get 9. 9 minus 9 is 0. 3 minus 3 is 0. So I get this does not exist, and we'll see why in just a moment. But what ends up happening is that we get a 7 here, an 8 here, and a 9 here. So what the heck happened? What the heck happened there at g of 3? Let me write in the rest of this because I'm type A and I want to see it there. What happened? Well, here's something kind of cool. The first thing you always do when testing limits, right? You test limits, you just plug in. You plug in directly, just substitute and see what happens. If you ever get 0 over 0, this is a special case, and we'll see it on the next slide. But basically what's happening here is I think you can agree that what I could do here is I could factor. And what's going to happen here is I have a hole here at t equals 3. There's a hole in the graph right there. So the graph from both sides is approaching something, but there is a hole where x equals 3. So what would it be approaching? Well, once I do this factoring and cancellation, it looks like g of t, after I do the cancellation, would just equal t plus 3 right here, right? So if I do a direct substitution and I do g of 3, I'd get 3 plus 3, which is, look at that, 6. So the limit is 6, even though the value doesn't exist at x equals, or excuse me, t equals 3. Let's keep going with this concept on the next page. Okay, so what comes with this this idea, and we kind of visited on the last example, is this idea of a one-sided limit. So the limits we just calculated are called two-sided limits. We evaluate it at that value, at the x value that we're approaching, or that a value. Now what we're going to do is we're going to approach from the left and the right. So a right-handed or right-sided limit, you'll see this plus, right? It'll be approaching a with a plus in its superscript. That just means approaching it from the right. So we're going to approach from the right. And then the left-handed limit, you'll see a negative symbol up there in the superscript. That means we're coming from the left. Okay, so pretty simple notation. Let's use that on our next diagram here. So using this graph, let's come up with, using one-sided limits, the values here for these limits. So here, this tells me I'm going to look at f of x, and I'm going to see what the y value would be as I approach -1 from the left. So as I approach -1, x equals -1 from the left, what am I approaching? I'm approaching 0. Okay, what if I approach -1 from the right? Well, if I approach -1 from the right, I get a different value. I get -1. Okay, what if I approach 1 from the left? Well, if I approach 1 from the left, x equals 1 from the left, my y value is approaching 1. What if I approach 1 from the right? If I approach 1 from the right, it looks like my y value approaches 2. And so on. If I approach 2 from the left, x equals 2 from the left, it looks like I'm approaching -1. And if I approach 2 from the right, it looks like I approach +1 for my y value. Just some basics of one-sided limits. Let's keep moving. Okay, so the existence of a limit. We just talked about two-sided limits. We talked about one-sided limits. The requirement in order for a limit to exist. So this limit to exist as x approaches a will equal L if and only if the left-sided limit here and the right-sided limit here both equal that value L. They both have the same y value for their limit as they approach that x value. So state each value or explain why it doesn't exist. Okay, so let's look at the diagram below and let's do the limits first. Okay, so approaching -4 from the left. Here's approaching -4 from the left. What does it approach? It approaches 2. How about from the right? So from the left and then from the right. These have to agree. So from the left it approaches +2. From the right it approaches +2. Therefore they agree. Therefore this limit exists and would be 2. Now, what is f of -4? It doesn't exist, right? There's a hole there. It doesn't have to exist for the limit to exist. The two-sided limits just have to agree. The two one-sided limits have to agree. So let's approach 1 from the left and 1 from the right and see if they agree. X equals 1 from the left is 4. X equals 1 from the right is -2. Therefore, this limit does not exist. Another way you could write that is a backwards E with a line through it. What is f of 1? F of 1 does exist, and it's 4, right? You can see the filled in circle there and the open circle there. Okay, the left-sided limit, the right-sided limit, and then we see if the actual limit exists as x approaches 6. So as x approaches 6 from the left, we get 5. As x approaches 6 from the right, we get 5. As x approaches 6, what is the limit? It is 5. But what is the output for f of 6? The output for f of 6 is 2. Now, like we had over here, it doesn't have to exist, or it could be just a jump discontinuity. That's okay. The limit still exists as long as the left side and the right side agree. Let's keep moving. Okay, a new function. Let's look at the greatest integer function. And this is the symbol for it. Okay, you might not be able to see it. It might be too small, but that's what we call the greatest integer function. This also is sometimes called the floor function. The y value will always be the largest integer that is less than or equal to the x value. So for example, f of 5 is 5, f of 5.3 is 5, f of 5.9 is 5, f of 5.9999 is 5. Okay, so I'm going to sketch it out, and then I'll come back and I'll explain. Okay, so here's a graph of the greatest integer function, or floor function as we call it. And as you can tell right here, I guess I could, let's see here. Can I use, no, I don't want to do that. Okay, anyways, I'll just explain as we go. Okay, so let's look at what happens when x gets close or near to 2. Okay, so let's look at from the left side. And then let's look also from the, I want to pick a color that'll show up, that color there, from the right as well. Okay, so let's diagram from the right first, seeing that I've got this color up. What would the limit as x approaches 2 from the right of f of x be? Well, it's approaching 2, right? Okay, and what is happening from the left side as x approaches 2 from the left for this function f of x? Well, it's approaching what? 1. Now, because the limit as x approaches 2 from the left is not equal, for f of x, is not equal to the limit for f of x as x approaches 2 from the right. Since those two aren't equal, this limit as x approaches 2 does not exist. Okay, but actually what we really wanted to do with this example is we wanted to expose you to this new function. You probably haven't seen it before, and if you have, you haven't seen it often. But it brings about this idea of the limit, right? We've got f of 2 right here. It exists, but our two limits from the right and from the left don't agree, and therefore there's this, and we're going to get to continuity later, but there's this discontinuity here as well. Okay, but just sticking with this idea of limits. Our limits, because our right and our left limit don't agree, they don't match, therefore the limit doesn't exist either. Okay, so I believe, yep, that's it. That'll be 2.2 notes. See you next episode. Have a good day.